Hey guys, so today we'll be building a kernel with the Hugging Face Kernel Builder. And this is really intended on being like a hands-on demo. So we'll jump right into the code and we'll start building our kernel and test it and see if we run into any problems. We'll figure out all that stuff together. So let's get started. All right, the first thing we'll do is we are in a directory called image to gray that I just made. There's nothing in here, as you can see. And we also are in this directory as in our VS Code editor as well. The first thing we'll do is take a look at the required files needed for a kernel. So here's a small example of kernel. This one's for ReLU, but you can see there's some files that we may need. First one is namely the build.toml. So let's add this file. Let's also add, I guess we'll need a directory for the torch extension stuff. Oops. And we'll have some binding files that are inside of the torch extension. And we'll also need a directory for our C source that happens to be called ReLU kernel here, but we'll call it C source. And we'll add a file to this called, I guess, image to gray too. No, CUDA. Cool. So now we should have some things in this directory that look much more like this. Okay. Oh, in the torch extension, we'll need a folder for the Python related stuff. So here we'll also make a folder called image to gray. And we'll also need to add a, oops, a init file to that because this is the location that will be imported as the library and kind of ties everything together so it's easy to use in the Python world. And don't worry, we'll get back to all this in a little bit as we iterate on the development. So the first thing that we'll need to do now that we have a directory is let's start to define our build.toml. And then after we've defined that, which really the build.toml is kind of like our package level, our project's package level directory or metadata. And we can define the name of the kernel, its dependencies, its sources, the intended targets, etc., things like that. So we'll start there. And then the next things we'll work on are the actual kernel, which will live inside of the C source, and then the bindings that tie these things together. So let's go over to our editor. We can see these files and folders that we've just created. So as I mentioned, we'll start with build. And I find it helpful to look at an existing example. So we'll head over to one of these kernels on the hub, and we'll open one of their build tomls. And we can actually probably copy and paste a big chunk of this and then change what we need. First thing is our project is called something different. So image to gray. It's not universal, meaning this is the flag for when you're building with a Triton kernel. And if it is universal, you won't need to specify much of this information down here, including like the backend and the CUDA capabilities. But in our case, we want to specify that this builds on CUDA, so we're going to set this false. For Torch, we need to include the bindings, which, as we created recently, live right here. So this just points to them. And then here we are defining the information specific to our kernel. So here we have kernel image to gray. Our backend will be CUDA. I don't think we actually need to specify the capabilities, and that whole list will be added for us, and we can just leave it blank. Additionally, I think this project we're copying from needed less. Yeah, so we'll just remove that. And then here you can see all the source files that were included. And in our case, we are only going to include this one file. Whoops, there we go. Because that's the only file in our kernel. So this is our build toml. Pretty short, straight, pretty descriptive, straightforward. Okay, next step. So now that we have an idea of the files that we need for the kernel, let's start to fill them out. First thing I think would be best is if we start to outline this actual kernel, then we'll know what the bindings, like we'll know which bindings are needed for the kernel to be used in PyTorch. So the first thing we can do is we should pulling up a different example and in some headers. So the first thing we'll want to do is we want to define a kernel that converts RGB to grayscale. And the other thing we'll do is define a wrapper for this kernel to align with the PyTorch extension interface. Exactly. So here, the first thing we'll do is we are going to, that is actually practically the kernel we want, but first thing we'll do is we'll set global, which indicates to CUDA where this should be defined. So next, this is a bit distracting. Next, we'll start to work on the image to gray kernel, which should take these constants, which are actually going to be pointers to our tensors, which we'll define here, and then the height and width. And just to quickly go through the logic, because I mean, this is not that very interesting of a kernel, but quickly going through the logic, we get the row and the column of the thread that's being executed from the specific block, specific thread in the block, from these values. And then we have this conditional statement that makes sure that we're not out of bounds because CUDA is going to execute this in parallel, and it's possible that the grid that we've defined to do the execution is bigger than the image that we're converting. So we need to make sure that the execution happens to pixels that exist. So that's what this check is for. And then here we actually are getting the index and pulling out the RGB of that pixel. And then finally, we have this small function that converts the pixel RGB by scaling them against different values to get a gray color. And then we set that back into the output. So what we need here is we need a wrapper, which will provide the correct types for our PyTorch interface. For example, the PyTorch interface will not accept an int. They only accept longs, and it won't accept an int8, a UN8. So let's have a wrapper that is void. And once again, Copilot has pretty much exactly what we need, where we are defining a wrapper for, I guess good is fine. We define this wrapper, which takes in a torch type, no longer a uint, and these are tensors. So we'll take in an input tensor and output tensor. We will get the width and the height from the input tensor, which is our image. We define these values are what tell CUDA like how much space to allocate and how much space to do this computation. So these are defined here based on the block size, which is set at 16. And then we call the kernel. And the kernel is called by actually pointing to the memory location of these tensors, of these input tensors and output tensor. And then finally called synchronize, which will make sure that all of the data is synchronized. And yeah, that should be a reasonable first start. We'll probably have to make some changes when we're building, but let's move on to the next file. So the next thing we'll need to do is we'll need to define a header for this for the interface. And conveniently, it's pretty much just the same header as the function of this wrapper we're calling here. And I think we may need to include torch here, as we did here, to make sure that we have the tensor type. Okay, I believe that's all we'll need. And then, so we have our build. Just gonna move this up. We have our build on the top. We have our kernel, which we've defined here. And then we have our binding header, which we've defined here. And then the last piece we need is our binding C++ file, which here will actually point to the header, point to the kernel definition, and register them for PyTorch to use later. So I actually think this also will be easiest if we look at an existing similar file. Maybe not. We'll borrow these headings. And then we can look at this part. So as you can see, this file has part up here, which actually are the wrappers, it seems like. And then down here, we have the library expanded where you can point to the actual definitions of the function, and we define the signature of those functions. And then the very last step is to register. So I'm just going to take that there. And we don't need any of those. We just have a single function, and it's called image to gray CUDA. But I guess we'll want to name it image to gray. I'll just get rid of the CUDA. And then we'll take the name of the function. This is the actual function name, and we'll put that here. This is pointing to this header, which is then pointing to this like this implementation. So next thing we have to do is make sure that our inputs are correct. So this is a void function that takes a tensor input output. So we define that there. And I think we may need to say that this returns void like that. Double check. Yeah, I think that's the correct syntax. Okay, cool. So we have our library defined, and then we have our extension register. Great. So this seems like the core parts. The last and one of the most important pieces is that we don't have a flake. And a flake is a Nix concept that lets us point to the actual kernel builder source code and then use that to build all the code that we've defined here. So far there's actually been no mention of the kernel builder in terms of like the actual code that runs to build stuff. We've just been defining things. So in the flake, which is at the root of all these projects, that's a bit of a complex one. Let's find a really short, simple one. We can copy this flake. So in the base of these projects, we'll have a flake, which is a, like as I mentioned, a Nix concept that points to the kernel builder, which is on GitHub. And then when we run our Nix command, it will use this file to fetch this information and then run the build commands, which are defined inside of here, which include figuring out how to build things based on this file. So now I think we actually are at the point where we will start trying to build things. So the first thing we want to do is jump into a dev shell. The command here is quite long, just because I'm choosing a specific shell to jump into. You can jump into any of the environments that you'd like. This is one of the powers of Nix, but in this case, I'm aware of my machine having a certain CUDA version, so it's going to run easily on this and quickly. So let's just start there. So we do Nix develop. We're going to use Torch 2.7 and with CUDA 11.8. And here, now we are in our environment. What we can do next, actually, we'll head over to the documentation and go to building kernels with Nix. What we'll do next is convert our build.toml file into the CMake files that the builder is using underneath the hood. And what we've done here is we've actually entered the development shell, and we'll be doing the steps one at a time so we can get a feel of what's going on. But most of these steps can be abstracted by just running Nix build, and you don't have to do the individual steps. So we're taking it more slowly here for everybody to understand the details. Okay, so we'll take the build to CMake command. We'll run that, and now you can see we've created a bunch of folders. We created a CMake folder, or a bunch of things, a CMakes file, setup.py, and a project toml, which are going to be used to build the extension. Next, we'll set up a virtual environment within our Nix sandbox. We'll enter that environment, and then we will attempt to build our kernel. And presuming there are no errors, the kernel will complete and it will be in our virtual environment with the name that we've defined in our build.toml. And based on the actual code we've defined, we should be able to convert an image from color to grayscale. I think we have a couple more steps for that. Namely, actually, one of the things that we haven't completed yet is the init file. So the init file is a Python concept, and when you import your library or a library, this is the first piece of code that runs. So at this level, we'd like to define this is where we wrap the kernel code into a nice, very like generally more easy to use Python function. So once again, we can go look for inspiration on the kernel hub. We'll go look for a, I don't know, short kernel, maybe this one. And go torch extension, meta blocks, init. We can see that the init file here imports the ops. These are what are going to be built by the kernel builder. And then it has headers with nice helpful comments. And then it actually calls one of the ops when you call this function. So we'll be doing something very similar. We're just going to copy the top of this, say init, and Copilot knows exactly what we want. So I'm not sure this is correct, but it wraps our image to gray. I think our image to gray function has a different signature though, so let's quickly look at that. Yeah, there's input and output. So what I think we'll want to do, not sure that we want all that. I don't even think we want these comments. What we want to do is, I think we're going to expect to be batch channel height width. And then we can grab that from the input. But we'll get back to that in a second. It looks like our kernel actually built without completely breaking, which is a surprise. And I think maybe the most useful thing will be to finish this function so we can call it from a small script in a second. So the next thing we'll do is we, I guess, can throw an error if there's not, like if it's not RGB, right? The whole point is to convert RGB to grayscale. So if there's not 3 channels, we will remove that. Yes, Copilot, thank you. The next thing we'll do is create a batch. We'll create a tensor of the same size, except instead of 3 channels, we'll have 1 because it's only grayscale. And then just for simplicity, we'll iterate over the batch. And no, I don't think we want to do that. We'll get a single image. I think we need to flatten, I think we need to change the shape and flatten it, which, yes, height width, okay. And then we need a single output, which is, I think, just going to be the height and width because the channel is removed, right? Okay, cool. So now we'll be able to call the method, the C method that we defined here, with our single image and our single output. And I think because the single output is just a reshape of this tensor, it will edit it in place, and the output should have the correct values. Great. So now let's make a new folder called scripts. We'll have a file called sanity. Just for checking. Let's put it down here. And in this file, we'll import torch. Then we'll import our new image to gray library. And let's just print all of the things from image to gray and see. Oops, see if there's anything of value. I'm not sure this will work. We may have to rebuild, but oh no, cool. So what we've done is we just ran that sanity script that we created, and you can see that we printed out the directory of image to gray, and you can see we actually have our function image to gray included on that. So I think the next thing we'll want to do is maybe we can use a real image, and with that image we can actually like check if this will convert it to grayscale. So oh, there we go. So I think we'll need to import some things. Import for images to handle images. First, we'll have to do the 1 second. Okay, apologies for that. I had to step away for a second. Where were we? Okay, we were trying to import a photo so we can make it grayscale. Great. So the first thing we'll need to do is import pillow for images, and then we'll import numpy just so it's easier to make that image an array. Image, just image open. I think we can just do that. Yeah. Then let's make it an array. And let's make it a tensor. Oh, think about that. So make it a tensor. What shape is this? Okay, so it's height width channel, yeah. Cool. So it's flip it around so it's batch channel height width, perfect. And then we should be able to pass this. Okay. So we should be able to pass it in and get the gray tensor, which will be batch one channel height width. I think, yeah, batch one channel height width. And then I think we can save the output image. I don't think that. I think we need to move it to the CPU. And I think we need to remove the batch. Maybe not. Why does it want to squeeze it? I think we just need to squeeze it once. I think we squeeze it, move it to the CPU, then move it. Yeah. Yeah, so now it's on the CPU in a numpy uh, array. I like numpy more. And now let's make an image. Okay. Output image or gray image equals the image from yeah. Yeah. And now we'll save it as gray one. Okay. So let's find out if this worked. Hmm. I should probably remember to put the image on the GPU. So I guess I can do that anywhere. Maybe I'll do it down here. Okay, didn't crash. So here, there was some issue with the tensor. So I got my image tensor, and squeeze it, and then I'm passing it here. I squeeze it, I get the shape, and then I put it on the CPU. So I'm gonna squeeze this earlier. I don't think I need squeeze 0 actually. Just do squeeze. And now I should have it be height width channel, okay? And then batch channel height width, and then okay, then that looks better. So why did it? Huh, strange. Okay, so one image is here, and one image is here. I wouldn't say that's grayscale. We probably have a bug somewhere. this seems okay. I guess we're creating the image, it's fine. So it's probably on like the math level, like at the kernel level. Right. So when we call this kernel, we are calling it height width channel. So height should be 0, width should be 1. Okay, so let's try installing again. So that will force the rebuild. I think that it's just the channels where we were just looking at the wrong channels, or looking at the wrong um, dimensions. And then we'll rerun our conversion sanity script right here, and it should save it as Grayscale. So hopefully this will come back right in, I don't know, a minute or so. There must be a way to speed this up. Yeah, we're running on a single core. Oops, that was the wrong process. Okay, so this is going to take a little bit of time because um, I think there's some environment variables that we'd need to set to speed this up that I'm unsure of at the moment. Which look like that. I don't see the jobs. Okay. We can be patient. This is painfully slow. Hmm. Let's see. Nice. Great. Okay, cool. Our kernel seems to work. I think we could improve on our build process for sure, but let's get this ready for pushing up and finalize some things that we would have to do if we were making this production ready. So right now, I just created I obviously initialized git repo, and now I made a git ignore. And the plan is to remove any of the development artifacts that we know we don't need. PyCache. Yeah, sure. I need this. But does any and ops and cmake. My project. Whoops. And set and registration. I think those are all the cool. So this is our image to gray kernel. Just to review, this is the actual kernel. This is the wrapper to make sure that we can accept PyTorch types. Then we have a header, which just tells our bindings the name of the PyTorch type signature we just looked at. Then our bindings actually include that, and we set up the Python level stuff, like the signature that would be expected in Python. We point to the function that's going to be called. And then in the init, we wrap that in Python, so we can actually call that with, generally setting up the expected inputs and outputs if you need to, or maybe mutating a tensor to be the correct shape, depending on your use case. And then we finally build it. So great, that's pretty much the end of the development cycle. The last part is just showing you in the production cycle, like if you were to build this and you don't want to jump into the sandbox, you can build it with the next build command. And here we're just specifying the jobs. Whoops. Now that we added everything with Git. Now that we added Git, Nix is aware of Git, and it saw that we haven't added any files to the stage, like Git stage files, so it doesn't know they exist. So now that we did Git add, and we can see, whoops, that we added those here, we should be able to run the next build command. So now this will do pretty much all the steps that we did inside of the development environment, but iterate across all of the different Torch versions that we support, CUDA versions we support, the CUDA capabilities that we opted to not specify in the build.toml. All those will be built and then placed into a results folder, which we then can upload to the kernel hub and share with other people. And then the point of that is so they can pull down the kernels and not have to build them themselves, which could take a bit of time, as you saw. So yeah, that's pretty much how to build a simple kernel end to end. This was the most simple kernel you can build, but I hope that's helpful. And I hope to see some of the cool kernels that other people build. Thanks.